In this tutorial, we will be discussing isomers. It is possible for organic compounds to share a molecular formula, but have a different carbon chain structure. These are called isomers, and there are several kinds. Isomers differ in physical and chemical properties. There are structural and constitutional isomers, which means that the atoms are arranged differently, but do not have a mirror image. And I realize you're confused by the idea of a mirror image right now, but we'll discuss those further on in the tutorial. Conformational isomers are groups of atoms that have different spatial arrangements. Subcategories include geometric or diastereomers. These isomers, once again, do not have a mirror image. And these are things like cis and trans around a double bond. Stereoisomers are isomers that do have a mirror image, such as D or L. And these are called enantiomers. So if we break isomers down to give you a visual, we have structural and constitutional isomers, and we have stereoisomers. Stereoisomers can be broken down further into enantiomers, ones with a mirror image and a chiral center, and diastereomers with no mirror image, such as cis or trans geometric, or conformers or rotamers. So let's talk about structural and constitutional isomers first. That's this category right here. These atoms are arranged differently. So if we look at the difference between butane and 2-methylpropane, both of them have 4 carbons. 1, 2, 3, 4. 1, 2, 3. The fourth one is branched off. They both also have 10 hydrogens. 3, 4, 5, 6, 7, 8, 9, 10. On the bottom one, 3, 6, 9, and then the 10th one is there. So they have the same amount and same kind of atoms, but if you look at them, they look nothing alike. Same with the names. The names are different too because the names reflect the different isomers. Then we have diastereomers, and those are like geometric, cis, and trans. The arrangement of like or same groups of atoms around a double bond. These are called diastereomers. So if we look here, here's the double bond. The carbons are going up, both of them. This is cis. If we look at this double bond, one's going up and one's going down. They're going in opposite directions. This is called trans. So stereoisomers are different molecules whose atoms are connected in the same order but have a different spatial direction, which is what we saw here with diastereomers. Optical isomers are molecules that are non-superimposable mirror images of each other. In order for that to happen, we're going to have a chiral center. And we'll talk about that in the next slide. Geometric isomers are stereoisomers that are not optical isomers. Once again, there's an example of one. With chirality and optical isomers, you have to have 4 different attachments coming off of that carbon. Notice we have an X, V, A, and R. If just 2 of those are the same, you cannot have a chiral center, and you cannot have an optical isomer. A chiral compound has at least 1 chiral carbon in its structure, and chirality plays an important role in biomolecules and drug manufacturing. Chiral compounds often can be classified as stereoisomers and have what they call handedness. So think of it this way. If you think of your hand, this is a really crummy picture of a hand. You have a mirror image of your hand. That's why you can't wear your left glove on your right hand. They are not superimposable. You cannot switch them back and forth. You can't put your left shoe on your right foot. They're not superimposable. That's the same idea of chirality. They're mirror images of one another. They're not identical. Alright, so let's talk about stereoisomers a little bit more. The chemical and physical properties are identical in many cases. Enantiomers, enantiomer pairs will have the same chemical reactivity in a non-chiral environment. In a chiral environment may show different behavioral properties. For instance, with light and polarizability. It can differentiate only by rotation of the polarized light. The light rotated to the right, or the light rotated to the left. Remember, light is in waves. So if we move the wavelength from one direction to another, the molecule might behave differently. Compounds that having mirror images are not superimposable. Enantiomers molecules have all the same physical properties except for one, which is how they rotate in the plane of a plane polarized light. Light that has been filtered so that only those waves traveling in a single plane are allowed through will rotate the plane the same amount, but in opposite direction. An equimolar mixture of the pair of enantiomers is called a racemic mixture. Racemic mixtures do not cause the light to polarize when it is shined through the mixture. Since half the molecules are rotating in the plane to the left and half to the right, the rotations cancel each other out and the racemic mixture does not rotate the plane. A non-racemic mixture will rotate the light. If it rotates the light to the right, it's considered D. If it rotates it to the left, it's considered an L. The amount of rotation can be used to determine percentages of an enantiomer in the mixture. And that is your explanation of isomers.